In this chapter, we'll talk about the introduction to Fourier series. Well, for future preparation, we would like to establish a few relationship among the integral formula. For example, on the screen you can see equation 1 on the screen, where it says the integral from 0 to the period t, capital T, of the function psi k omega naught t is equal to 0. Similarly, the integral from 0 to the period t of cos k omega naught t dt equal to 0. That we have to prove it later on. Equation 2, it says the integral from 0 to capital T, which is a period, of the function psi square k omega naught t, or the integral of cos square k omega naught t is equal to capital T over 2. In equation 3, it says the integral between 0 to the period t of the function cos k omega naught t times psi of g omega naught t is equal to 0. And in that equation 3, notice that the integer k and the integer g, they are different in general. Similarly, the equation 4, it says the integral of psi k omega naught t times psi g omega naught t dt equal to 0. That is what equation 4 said. And again, this is the case for in general k and g, they are different. Equation 5, it says that the integral of cos k omega naught t times cos g omega naught t is equal to 0. So those are the 5 basic equations that I'm going to prove to you, so that in order to establish some useful relationship for future development. Oh, in the previous slide, the omega naught is considered as the angular frequency, and that is equal to 2 pi times f. That is shown in equation 6, where the frequency f is defined as the reciprocal, or 1 over t, reciprocal of t, 1 over t, and t represents the period of the function. Equation 8, it gives you the definition of the periodic function f. If you have a function f, and we call that function f is a periodic function, if this is true, the function f at time t, small t, is equal to the value of the function f at time small t plus capital T. In other words, after a period of capital T, the function is repeated itself. Let us go through example number 1. Basically, in this example, we will try to prove that equation 9, we're going to try to prove to you that this integral psi of k omega naught t should be equal to 0, as I told you earlier. And the way to prove it is just let that integral equal to a, and let's try directly to evaluate that integral. And we all know the integral of psi is equal to negative of cosine. And then because of the chain rule, we have to multiply with the factor in the front, which is 1 over k omega naught. After we find out that integral, we have to evaluate between the upper limit, which is capital T, and the lower limit, which is 0. So if you substitute the upper limit and the lower limit, we can evaluate the value of a. Okay? So for example, when the small t equal to the upper limit, capital T, and minus the small t equal to the lower limit, 0, this is what you got, equation 10. And then obviously cosine of 0 is equal to 1. And furthermore, we also know that for any integer value of k, could be 1 or 2 or 3 and so on, cos of k 2 pi is also equal to 1. And because of that reason, a is equal to 0. So in other words, a is equal to 0 means that this integral of sine k omega naught t dt between 0 to t is equal to 0. And this is the one that I stated to you earlier, and now I just prove it to you through example 1. So let's take a look at another example, example 2. In example 2, we would like to evaluate the integral from 0 to the period capital T of the function sine square k omega naught t. So that integral, let's say we call it equal to b. Now, it may not be easy to integrate the function sine square. However, from high school trigonometric relationship, we can see according to equation 12, sine square of an angle can be expressed in terms of a double angle as shown in equation 12. So sine square is equal to 1 minus cos of 2 alpha divided by 2. Using the relationship expressed in equation 12, then we can replace sine square of the angle in terms of cosine of the double angle. So substitute equation 12 into equation 11, then we can see we obtain equation 13. Now, if you look at equation 13, you can see it is very easy to evaluate the integral, because the integral of the first term, the integral 1/2, is just simply 1/2 times t. And the integral of the second term, which is involved with cosine of an angle, it should be straightforward. So we can evaluate the integral shown in equation 13 very easily, and then after that, put into the upper limit capital T and the lower limit 0, then equation 13 will become, as shown on the screen, this equation right here. And then finally, if we substitute the value of small t with the upper limit, which is capital T, and then subtract the value of small t with the lower limit 0, immediately we will get equation 14. So look at the equation 14. This is what we got. B equal to t over 2 minus 1 over 4k omega naught times sine of 2k omega naught t. That is equation 14, which is very straightforward. And then equation 14 on the previous slide, as you can see, can be simplified or rewritten as shown in the next slide right here. And notice that the second term, regardless of the integer k, is equal to 1 or 2 or 3, any integer value of k, it will make the sine term of 2k times 2 pi, that always turn out to be 0. And therefore, the value of b is just simply equal to t over 2. And according to the previous slide definition, the b is defined as sine square of k omega naught t, as shown in equation 11. Sine square of k omega naught t, okay? So this is the integral of sine square k omega naught t dt between 0 to the period capital T. That is the definition of B. And we just proved to you that that is equal to T over 2. So that relationship that I stated to you earlier, I have just proved it again through example number 2. The next example, number 3,